Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
He's going to talk about group strategy proof mechanisms for Steiner forests.
Okay. So we study the problem of sharing the costs of the Steiner network between a number of users that are just motivated by selfish interests. Let's briefly introduce cost-sharing mechanism. So in our case, we have a service provider, and a set of potential users. Every user has his own private utility for receiving the service, meaning that UJ is the largest price willing to pay to get the service. In our case, that will be to be connected in a network. Moreover, for every subset of users, we'll have a function that is a cost function that will be the cost that will incur the service to connect this subset of users. So this is usually an optimization problem, and it's also an NPR optimization problem. It's an optimization problem that is not easy to solve, computationally easy to solve. So what is the cost-sharing mechanism? So it's going to receive a bits from every user, and that is the price the user is willing to pay to get connected. And this bids is not necessarily equal to the utility. So it may lie. So that's a very fundamental issue. And the goal is that the cost sharing will report a set of users that will receive the service, subset Q, and a payment for every user, payment PJ. That is the price you will have to pay. And you may assume that if the price is less than the bid, is not going to get the service. Is the price? I mean, he's going to accept the offer. If the price is higher than the bid, then he's not going to accept the offer. And the goal of this provider is that of distributing the cost. So he wants the users to pay for the service they are going to get. Try to collect as much money as possible from the users. So what is the user point of view? This is the mechanism point of view, right? Now let's see the user point of view. The user is just motivated by maximizing the payoff, right? So utility minus price. So if we'll get the service, it will have a benefit uj minus pj. If we won't get the service, then we'll just get 0. That's it. The issue is that users may lie about the utility because this will allow to have a higher payoff. So just interrupt me if it's not clear enough for these first steps that are a bit compressed, bit dense, right? So which are the objectives of such mechanism from a more formal point of view? So the basic requirement is this mechanism is strategy proof. So it's such that I'm going to incentivize users to cooperate. The form of cooperation we want to implement is to reveal the true utility. So to reveal the private information. So the dominant strategy for every user is just to be the true utility. There is a stronger form of truthfulness that is group strategy proof, meaning that the same holds even if users cooperate among them. They exchange information. They talk each other. So that's just exchange of information, because if we want to allow a stronger form of cooperation, the whole system just crashes. So everything I'm going to say doesn't hold. So this is but they may talk each other. So but everybody still the individual objective is still maximizing uj minus pj. So we are not going to talk about a collective utility in some sense, right? So that's just okay. Then we want to achieve cost recovery. That is the sum of the prices that I'm going to charge all users is bigger or equal than the cost of the solution. This is the solution for the subset of users that will get the service. And also there is another requirement, that is competitiveness. Competitiveness is that the sum of the payments is less or equal than the optimal solution. So why competitiveness is important? Because otherwise the users may just say, we'll do with another provider, or we'll do ourselves, right? We don't have to accept your service because it's not good enough. Okay, since C could be computationally hard, we have that in ensuring cost recovery and competitiveness maybe not easy from a computational point of view. But that's not the only problem. Actually, ensuring competitiveness and cost recovery may not be easy also because we want to have group strategy proofness. And we will see later about this. So what we are going to do is to relax one of these two constraints. So either relax competitiveness, meaning that I'm going to recover the old cost, but the sum of the prices is at most alpha times the optimum, or in exactly the same way, I'm going to achieve competitiveness, but the sum of the prices are going to recover only an alpha fraction of the cost. I can scale up price or scale down, and I can move from one to the other. Now, assume that I'm going to distribute the real cost the provider is going to incur, but I relax competitiveness, then I accept to have the price to be, the sum of the price to be alpha times the optimum. Okay? Since this is going to recover the cost, if I scale down by factor alpha, I have something that it's a lower bound on the optimum. Right? Is it clear? Yeah.
So when you scale down the prices, the benefit to the user changes, right? So there could be issues of, say, if you satisfy cost recovery initially, if you scale them up, then it's no longer a strategy improvement.
Right. So that's true. So we should try to take one of the two point of view, right? From the point of view of the analysis that will follow, that will work well anyway. But I agree with you. So we can, once I have a set of users that accept my bit, I can scale up or scale down. So in this talk, we are going to talk about a network design problem that I guess all of you are familiar with, the Steiner forest. With the Steiner forest problem, we have an undirected graph with positive costs on the edges and a set of terminal pairs. So set of terminal pairs, and the goal is to compute a minimum cost Steiner forest such that for every pair there exists a tree that contains both S and T. Okay? So I'm going to ensure connectivity between every terminal pair. Right? And in general, this will be a forest. Special case is the Steiner tree, in which we have a set of terminals, and I'm going to connect all terminals to a specific source. What is known for the Steiner forest problem? So Agrawal, Klein, and Ravi proposed a primal dual two approximation algorithm for the problem, and this technique was later generalized by Gibbons and Williamson to a wider class of network design problem. From the game theoretical point of view, group strategy proof cost-sharing mechanism have been proposed by Jain and Vazirani in 2001 for the Steiner tree problem. And this mechanism satisfies cost recovery and two competitiveness. There are very few such results. There have been a couple of results last year by Martin Pal and Eva Tardos. They also presented a three competitive cost recovery algorithm for facility location and a constant competitive cost recovery algorithm for the single thing rent or buy problem that I'm not going to design. So, but till now we were not able to extend this mechanism or to propose a new mechanism for the Steiner forest problem. And in this talk I'm going to present a group strategy proof cost-sharing mechanism for Steiner forests. And that achieves the same approximation bound of the best approximation algorithm. And so how do we achieve a group strategy proofness? So a direct way of achieving group strategy proofness is by designing a cross-monotonic cost-sharing mechanism. What is a cross-monotonic cost-sharing mechanism? So it is a cost-share mechanism. So key Qj is the cost-share assigned to user J once the subset Q is served by the mechanism. And so that's our goal. So assume we compute such cost share. So this function is said cross-monotonic if each individual cost share does not increase if additional players join the game. So if I'm going to enlarge set Q, key J, the cost share of user J is going to decrease. So basically, this also works the other way around. I'm going to kick out some player, then all other players will only have the higher price, only receive the same service at a higher price. And so for every subset of user Q prime, for every individual user, the cost share on Q prime is only higher than the cost share on Q. And the theorem of Munich-Schenker says that if I have a cross-monotonic cost-sharing mechanism that is competitive and cost recovery, then I also have a group strategy proof mechanism that is competitive and cost recovery. And it's the implementation is very simple. I start from the whole set of players, then run my cost-sharing mechanism, publish price, and I'm going to drop who is not willing to pay this price, and recurse, so on and so forth. Good. So we will concentrate on designing a cross-monotonic cost-sharing method. Primal dual algorithm, cross-monotonic cost-sharing methods are usually based on primal dual algorithm because there is a very natural interpretation of dual variables as prices that I'm going to charge the users. Let's catch the primal dual algorithm of Agrawal, Kleiner, Ravi. So any primal dual algorithm will maintain, while we construct a solution, will also maintain a feasible dual, right? And the key trick is to use the feasible dual, to bound the cost of the primal solution by weak duality, right? So let's write a primal dual for Steiner forest, and this will be just the dual that is used by Agrawal, Kleiner, Ravi, and Gemmas-Williams is just the standard undirected cut formulation, in which we associate a variable xe to every edge e, and then we have this notion of Steiner cut. So the Steiner cut is a set of terminal that is going to separate at least one terminal pair. Okay? And you may easily realize that every Steiner cut must be crossed by at least one edge in the Steiner forest. Otherwise, there will be a terminal pair that is not connected. So the primal LP consists of minimizing the cost of the edges that I'm going to pick in the forest, subject to the constraint that for every Steiner cut, is crossed by at least one edge in the solution. And I'm going to relax the integrality constraints to obtain a dual formulation in which I associate a dual variable to every cut, and I want to maximize the sum of the dual variables, subject to the constraint that for every edge, the sum of the dual variables of the cuts that are crossed by this edge is less or equal than the cost of the edge. Is it clear? Because I will discuss a lot about this formulation, and okay, this is very well known, I guess, to all of you, and we'll define by delta U the set of edges that is crossing cut U. There is a pictorial view of this algorithm in which we interpret a dual variable as a disk or radius YU, given a cut U. We draw a disk around cut U of a radius equal to the dual value. And the primal dual algorithm will raise dual variable for Steiner cuts till some edge becomes tight, and then this edge is picked in the solution. So this edge is cost 4, and once the dual variable for Steiner cut S and T sum up to 4, then this edge is tight. I'm still dual feasible, and I can accept this edge in the solution. We'll see an example, more sophisticated example. So the Agrawal-Kleiner-Ravi algorithm will initially grow dual variables for singleton terminals, right? At this point, this edge becomes tight. Now I will merge these two modes, and then I will raise a dual variable for the Steiner cut formed by these two modes, because this is still a Steiner cut, as one has to have their mates in other components. So I keep on going, keep on doing. Now this edge becomes tight. Then I'm growing dual variable. I'm picking this edge in the solution. Then this edge becomes tight. This is still a Steiner cut because S3 is inside, T3 is outside, right? And then at this point, these two modes collide, and I'm going to buy this path. The difference between the Agrawal-Kleiner-Ravi algorithm and the Gemans-Williams algorithm is that Agrawal-Kleiner-Ravi is going to buy a path at every relevant event, while Gemans-Williams will buy all tight edges, and they will prune back. These are basically, this is basically the same algorithm. They are very similar algorithms. But we will use the point of view of Agrawal-Kleiner-Ravi. Okay, the analysis of Agrawal-Kleiner-Ravi says that the cost of the forest is at most 2 times minus 1 over k, a feasible dual, and this is therefore by weak duality a 2 minus 1 over k approximation. The analysis uses one trick, that is the following. So basically we are going to use twice the dual to pay for the forest, and the reason is the following. If two modes collide, the cost of this edge is just equal to a real dual, right? So to the dual of this cut plus the dual of this cut. But this component may be traversed by other paths, right? But the cost of traversing this component is given by the cost of going from the border to the nearest terminal, and from the nearest terminal to the border, that is, again, equal to the total dual inside. That's basically the proof, right? I mean, one should be more careful. It's a bit more complicated, but this is the idea. Okay, so let's try to use this idea to design a Costsharing mechanism. So we say that the terminal pair is active at time t if S and T are not in the same mode. In this case, for instance, S1, I mean, all these terminals are active, right? Now,
What's a mode?
a mode is a disk,
Okay.
a disk. So now we'll grow active modes by epsilon, and the first idea is that of sharing equally the dual among all active terminals. That are all those guys that are interested in growing this mode. So S1 will get a third of the increase of the dual variable, epsilon over 3. T2 and T3 will get epsilon over 2. T1, it's alone, then we'll get just epsilon. Great. Then some notation. Let's define by UTR the mode that contains terminal R at time t. Okay, this is, for instance, the mode containing terminal S1 at time t. And then we define the number of active terminals in the mode contained by R at time t. So A S1 ATR S1 is equal to 3. Now the Costsharing can be defined as the integral between 0 and the time in which a terminal is not active anymore, that is in the same mode of its mate, by 1 over the number of active terminals in the. That's just the whole notation. And then the Costsharing of a pair is just the sum of the Costsharing of the two terminals. Great. Now, I show as an example that this is not cross-monotonic. So this example is very simple, as just 3 terminal pairs. And the cross-monotonicity, again, is if I'm going to kick out a terminal pair from the input instance, the Costsharing of every individual user must just go up, cannot be reduced. That will be more expensive. Okay, then I'm going to execute this primal dual algorithm. And now at time 0.5, we have that all these terminals will be in the same cut, and that's not a Steiner cut anymore, right? So I'm going to buy these 3 edges. On the other end, S and T must still connect, and then I will raise the dual variable for these 2 Steiner cut. Then they will pay 2.5 each. So at this time, the path connecting S to T is tight. That means that this path will fill a total dual equal to the cost, right? Because the dual that this path fills from every of these components is 2 times the dual. Now let's do the following. Let's take S2, T2 out. And then we can observe that the S1 and T1 will meet only at time 1.5, right? Yes, at time 1.5, right? But at the same time, S and T meets. Then the Costsharing of S and T is 3. So I've taken out a pair, and my Costsharing has decreased. So this is not cross-monotonic. Why this is not cross-monotonic? So the idea is that the activity time, that is the time S and T are active, depends on S2, T2. Depends on another terminal pair. And so the idea is to get rid of this dependency. Then we should let terminals to be active for some fixed time that does not depend on other terminal pairs. Now, in this example, the idea will be to assign activity time to S and T equal, for instance, to half the distance between half the cost of the ST path. Actually, we spent quite a long time trying to identify a simple and clear concept, and in the end, the simplest concept you may think of is the right one. But then it won't be so easy to see that that's not going to screw up the approximation. That's a major point. So now I define the concept of dead time for every terminal pair as the distance between the two vertices over 2. Very simple. And then every terminal will be active up to this point, even if we are constructing a non-dual feasible, a non-feasible dual solution. So again, terminal I defined, so the dead time of every terminal as half the cost of the path connecting to its mate. And then the Steiner force algorithm will just grow modes until there is an active terminal inside, even though this is a non-Steiner cut. The cost share is determined exactly as before, with only one difference, that the integral is until the time, I take the integral from 0 to the activity time, to the dead time of the terminal. Not just the time when the terminal gets satisfied, but even more. In this case, for instance, you may observe that S2 and T2 are happy at time 0.5. The distance is 1. S1 and T1 are also happy, but I keep on growing. I keep on growing until time 1.5, right? And at time 1.5, even S and T are happy. And but even if they are happy, I keep on growing. And I grow until time 4.5. The cost share of S and T is actually not 9, but it's 6. Because so there's a mistake here. Because I collect 3 in the first phase, and then I collect 3 because I'm growing the non-Steiner cut containing S and T for 3 more time units. Anyway, that's the idea. And then if I take out S2 and T2, I have exactly the same cost share for S and T. S1 and T1 will pay more. S and T will pay just 6. And we can easily prove that this is actually cross-monotonic, because if I'm going to take out a terminal pair, I will have, so R dot is R minus ST. I'm going to take out terminal pair ST. Now I'm going to prove the cost share of every other terminal is just going to increase. So I denote by AT0R the number of active terminals in the mode of R at time t. And what I have is that for any terminal, for any time, the mode of the execution or R dot is included in the mode of the execution on R. And then there are less terminals inside. And since the cost share is determined by 1 over the number of active terminals inside the mode of R, this is only going to be larger for R dot. And the upper limit, the endpoint of the integral is the same, because it doesn't change. So far, so easy. The problem is that now to prove that the cost share, that I'm going to have a good approximation. And actually, we are able to prove that even though this dual is not feasible for the Steiner cut, undirected Steiner cut relaxation, the sum of the duals is still a lower bound on the optimum. So even though I'm going to grow in components more than in the classical Steiner forest algorithm, I'm going to get still a lower bound on the optimum. So the cost of the forest is still 2 times the dual, that is equal to 2 times the cost share, but should still prove this. So now I'm going to prove that this is less or equal than 3 over 2 the optimum in a couple of slides, and then we'll briefly move on, and I will also prove this, but we'll first see how we can change the linear programming formulation for the problem. So let's see how can we bound the sum of the cost shares. So we define an order between the terminals, just the order given by the death time. So half time the cost, the mean cost path between the two terminals. And now for every mode, so consider a component, I say that terminal V is responsible for that component at time t if it is the terminal of higher rank. Okay? If it is the terminal in the component that has further distance to its mate. It's a very simple notion. Now define the responsibility time as the total time a terminal is responsible. So this may end before the death time because it's going to meet with another terminal that has bigger responsibility, bigger death time, higher rank. So this is a different definition of cost share. So I'm going to not share the cost, but to give the whole cost to the responsible guy. This is still exactly equal to the dual. And this is also cross-monotonic. So this is still cross-monotonic. And you can easily see that the sum of the cost shares that is equal to the sum of the dual is exactly equal to the sum of the responsibility times. And now let's see whether I can bound the sum of the responsibility times. So for doing that, I'm going to take the optimum Steiner forest and every tree in the optimum Steiner forest. And then V1, Vp are all terminals that are connected by this tree. Are all terminal pairs that are connected by this tree. We must have the following that, so let's consider at time t all active components containing these terminals. This is the component containing terminal Vi plus 1 up to Vp. And these are all pairwise disjoint because there is only one active terminal in each component. So this is the situation at time t. I have 3 components, but three components, and for every component a responsible person, responsible guy. Now, what you can observe is that every component just loads a different part of the tree, right? So this epsilon growth will load, I mean, we can account all the dual growth, and the sum of the dual growth of the components is just less or equal than the cost of the tree, because this tree is bridging together the component. So a epsilon increase will just load a new part of the tree, a new part of an edge. Actually, this is not true. This is true if there are at least two components. But if there is only one component, and between Rp, so between RVP minus 1 and RVP, there is only one component, because only one guy is left. Okay? Then this is enough to prove that the sum of the responsibility times, so the first P minus 1 terminals, is less or equal than the cost of the tree. But still, we miss to take into account the responsibility time of the last terminal. And this is quite easy, because this is at least the distance between the terminal pairs. Let's say that this is the responsible pair. And the alpha the distance is at least equal, at most equal to half the cost of the tree. Right? So the death time is half the distance, that is half the cost of the tree. And then we end up with proving that the sum of the responsibility times is at most 3 alpha, 3 over 2, the cost of the tree. And this will give us a 2 approximation. So as I told you, I can get to actually 2 approximation, then prove that this is a lower bound on the optimum. But now, actually, there is maybe a more interesting issue here. That is, I'm obtaining a non-feasible dual. So the question is, does it exist a linear programming relaxation for the Steiner forest problem, for which this is a feasible dual? And so we answer positively to this issue. And then we present a new linear programming relaxation for Steiner forest that is strictly stronger than the undirected cut relaxation that has been used in all approximation algorithms. Okay. So actually, we can observe that our dual is strictly stronger than the undirected cut dual. Consider this example as 1, as 2, as k minus 1, and these are the mates, right? Okay, the optimum is 2k minus 1. We are just to buy a path from S1 to T1, while the standard Steiner forest dual is k, because once I have at time 0.5, I just buy the whole path. That's it. Our dual is 2k minus 1, because once all terminals are in the same component, I'm going to grow a non-Steiner cut for T1 and S1 by half the distance. So the cost is k minus 1 plus k, and this is surprising matching the optimum. So it seems quite interesting situation. Let's try to define a different linear program. So we still order terminal pairs by death time, and we associate every cut with one single terminal. For a Steiner cut, we just take the terminal that has highest rank. So then we are going to define the set of Steiner cut that are associated with specific terminal, W in this case. But we also raise dual variables for non-Steiner cuts. And this is a non-Steiner cut is associated to the terminal pair or largest rank, highest rank inside the cut. Now I'm going to define this dual linear program in which I maximize the sum of the dual variables for both Steiner and non-Steiner cuts. And for every edge, I still require that the sum of the cuts that are crossed by this edge is less or equal than the cost of the edge. But I have this additional constraint. For every terminal, the sum of the dual of the non-Steiner cuts, and of the Steiner cut, for which W is responsible, is less or equal than dW. Okay? So basically, I raise dual variables containing one specific terminal, at most up to the death time of the terminal. And this is distributed between non-Steiner cut, Steiner cut, and non-Steiner cut. So capital U, V, W, W bar is the set on non-Steiner cut for which W and W bar are responsible. And now I'm going to write the primal for this corresponding primal. And the corresponding primal will have a variable for every edge and for every terminal. And we seek for minimizing the sum of the cost of the edges plus the sum of the death times for the terminals, right? subject to the constraint that for every terminal and for every Steiner cut, the sum of the that every Steiner cut, you see, is so the sum of the is crossed by at least one edge. No, that's not true. Sorry, the sum of the x variables for the edge is crossing the cut plus xw, that is the variable of the terminal that is responsible for the Steiner cut, is bigger or equal than 1. What does it mean? That I either cross a cut with an edge, or I select the responsible terminal inside. For every non-Steiner cut, I write a constraint saying that the sum of the variables for the edge is crossing the non-Steiner cut plus the x variables of the two responsible guys bigger or equal than 1. So this may appear complicated, but it's quite simple, because you may see that every integral solution has a Steiner forest that is less expensive. So basically, this is a primal for the Steiner forest problem. Consider a cut. So if this cut is crossed by an edge, fine, right? If it is not crossed by an edge, this may not give rise to a feasible Steiner forest. But actually, if it is not crossed by an edge, we have to set this variable equal to 1 for the responsible terminal inside. But complementarity, I know also that the complementary cut is not crossed by an edge. And then I have to set x w bar equal to 1. And then I'm going to pay dw, 2 times dw in the optimum solution, in the objective function. But then I can connect these two terminals with, I can buy all edges on the path. And then I get a feasible Steiner forest. Okay, I'm almost done. We prove for this linear program that the optimum of the undirected cut formulation is always smaller than the optimum for this linear program relaxation, and this is less or equal than the optimal Steiner forest. The proof takes 1 minute. I consider an optimal Steiner forest and every tree of the optimal Steiner forest. This is a component in which I pick the responsible pair. This is the path connecting the responsible pair, and these are the other edges of the tree. Now I show you a feasible solution for the primal that has cost less than the optimum, and I assign xw equal to 1/2, xw bar equal to 1/2. All edges on the path have xe equal to 1/2, and all edges that are outside the path, xe equal 1. So let's see the objective function. The objective function is bounded by ct. So this is a sum xe ce plus xw plus xw bar times dw. Sorry. xw plus xw bar times dw. That is equal to ct minus half the cost of the path, since I have only 1/2 on these edges, plus 1/2 the distance between w and w bar. But this is less or equal than the cost of the tree. So this is better than the optimum, and also all constraints are satisfied. So let's look, for instance, the Steiner cut. If the Steiner cut will contain W, then this constraint is satisfied because I have xe equal to 1/2 for one edge crossing the cut, and xw equal to 1/2. They sum up to 1. If the Steiner cut does not contain W, but does intersect the path, then there are at least 2 edges with xe equal 1/2, and these sum up to 1. And if the Steiner cut doesn't intersect the path and doesn't contain the W, then we'll cross one such edge. And then, again, this is satisfied. For non-Steiner cuts, the same holds, but a non-Steiner cut may just include the whole tree. But that's still fine because I have xw equal 1/2 and xw bar equal to 1/2. And then, you see, I sum up xw plus xw bar, and this is bigger or equal than 1. So this is a stronger linear programming relaxation for Steiner forest. And of course, okay, we proved also that there was a recent paper in SODA proving lower bounds on the competitiveness of cross-monotonic cost-sharing methods. And they proved 3 for facility location, then matching the result of Pilot-Tardosh, 2 for the edge cover problem that is actually not that an interesting problem, but vertex cover they proved n to the 1/3. That's very, very much far away from the best approximation. But for proving this lower bound, we use the so-called core property. That is that for every subset of the user, the sum of the cost shares must be less or equal than the optimum solution for this. Okay. So this is based on the use of the core property. So we also proved that for the Steiner tree algorithm, it's not possible to do better than 2. So the result of Jane and Vazirani and our results are tight, and they are the best possible. Okay, this is the instance, but I'm not going to. So the most challenging open problem is that if we can use our better dual for improving the Steiner forest approximation. If on some instances we do much better than the standard dual, there are instances in which the integrality gap is just 2. So one should really try to characterize the good instances and the bad instances and deal in a different way with the bad instances. And finally, it would be nice to give cross-monotonic cost-sharing methods for other network design problems. And actually, this is we have only very few results. We have 3 or 4 results. And also, it would be very interesting to characterize those problems for which it is possible to give a good cross-monotonic mechanism, and those for which it's not possible. And this is very much different from a traditional approximability. So I think there are lots of very interesting open problems. Thank you. Thank you very much.
So these lower bounds apply only to cross-monotonic cost-sharing methods. So you could conceivably have group strategy proof mechanisms which are not.
So they extend to group strategy proof mechanism under some restrictions. One restriction that there are no free riders, meaning there are no users that just receive the service for free. And then there are one other restriction on the kind of function you have. I mean, there is a discussion in the paper by Murli Kamadian and Mirokni about how to extend. I mean, actually, Murli and Schenker says that there is a if and only if relation, but it's probably not true. You may have a group strategy proof mechanism even without plasma. This is another very interesting open question. Okay, thank you.